All right, ladies and gentlemen, I told you that this pretty much was going to be a quick chapter, and without doing a whole lot of labs, we're flying through it. The two major things in this chapter have been the entropy and calculating Gibbs free energy. And we're actually going to be focusing on the Gibbs free energy part of this again today. And what we're going to look at is two different things. We're going to look at free energy and how pressure affects that. And then we're actually going to bring in the equilibrium constant to this as well. So we'll get started here with looking at how pressure affects free energy. So we're looking at the dependence of free energy on pressure. Now, first of all, when we look at pressure, does pressure affect the enthalpy? And remember, enthalpy is heat. So if I increase pressure or decrease pressure, does that have any effect on heat whatsoever? And the answer is no. It does not affect heat in any way at all. However, if you look at pressure, would it affect the entropy of a gas? Well, if you think about that, if you increase the pressure, what do you do to volume? And what you do to volume is you actually end up decreasing the volume. Well, if you are decreasing volume, if you're going from a large volume to a smaller volume, you're decreasing the space that those particles can take up. So basically, pressure is going to affect the entropy of a gas. So if you compare 1 mole of a gas at 10 liters, so we have 10 liters, versus 1 mole of a gas at 1 liter, so small 1 liter, okay, which one is at greater pressure? And the 1 liter right here would be at a much greater pressure than the 10 liters would. Again, it goes back to space. You'd have a lot of space for those particles to be in versus not a lot of space for the other particles. So the larger the volume, the more entropy that you would have. So the gas has more positions available at 10 liters versus the 1 liter. So ultimately what happens is entropy is greater at larger volumes. So short story is pressure definitely affects the entropy of an object, which is going to ultimately affect the free energy, okay? Because free energy is directly dependent on entropy. It's dependent on heat as well, but we just said heat doesn't matter. So now, getting into this, okay, we're just going to throw an equation out here, okay? So what we're looking at is, without a whole lot of details, how do reactants and products not at standard conditions affect free energy? So we've done some things in the past where we've come up with equations not at standard conditions. So what this equation here is, it's Gibbs free energy when you are not at standard conditions. If you want to know where this equation came from, there's 2 pages in your textbook. Go look, okay? It will tell you where that equation came from. But what this equation stands for is now this delta G here is the free energy for a specific pressure, because we've been doing this under standard conditions, and standard conditions is 1 atmosphere of pressure. Well, now we can do this under any pressure. The G0, this term, okay, is the free energy under standard conditions. That means you still have to calculate the free energy using the sum of the G's of the products minus the sum of the G's of the reactants. So this may still have to be calculated in problems. Q is our reaction quotient. And remember, our reaction quotient is still the concentration of products over the concentration of reactants. But instead of the equilibrium position, it's your initial conditions. Okay, so, and we just did a whole bunch of that in the last chapter. R, now is your gas constant. And notice it's this weird one that just shows up every once in a while for no reason, 8.314. And then T is the Kelvin temperature. And ultimately, ladies and gentlemen, this becomes a plug and chug problem for us. There's not a whole lot we're going to do with this except find one of the missing variables. So when we use this equation right here, okay, you should write this on your AP Chem equation sheet because I don't think it's on there. But it honestly is a plug and chug. Most of the time we're looking for this, but we can try to find the standard, but we have a way to calculate that. Or we could find a temperature that something would occur at. Most of the time you'll be looking for this or a temperature that something occurs at. So, quick problem with how to use this. One method of producing methanol involves reacting carbon monoxide with hydrogen, and we want to know what is the delta G when we've changed the pressure. So our pressures are at two different pressures other than atmospheric. So the pressure of carbon monoxide is 5 atms, and the pressure of hydrogen is at 3 atms. Okay? So what we want to do is we want to use our equation delta G equals delta G 0 plus RT natural log Q. So there's a few things that we're going to have to calculate. One of the things that we have to calculate is what is delta G. So we have to do a side calculation to find G0. And that's going to be the sum of the G's of the products minus the sum of the G's of the reactants, which means you're going to have to take your equation, your thermodynamic sheet, and look all of these up. I'm going to tell you what they are real quick. This is minus 137. This is 0. And this is minus 166. So the sum of the products minus the sum of the reactants would be minus 166 minus a minus 137, which is going to be a plus. So your delta G for this comes out to be minus 29 kilojoules. Okay, so we have the delta G. Now, so of our equation, we have this term. Now we need the Q. And the reaction quotient is the equilibrium constant. But remember, the equilibrium constant expression we would have to write is going to be 1 over, and actually this is going to be pressure, 1 over the pressure of CO times the pressure of H2 squared. Okay? And it's a 1 here because that's a liquid. So, putting in these values, we would have 1 over 5 times 3 squared. So that Q, doing that math, comes out to be 0.022. So now, you've got your Q calculated. So the longest part of this problem is calculating everything that you need just to actually do the equation. So my equation is delta G equals delta G 0 plus RT times the natural log of Q. And plugging everything in. So delta G equals minus 29 plus 8.314 times 298 times the natural log of 0.022. And I'm going to assume that you can do math. So the Gibbs free energy of this comes out to be minus 38.5 kilojoules, which then basically means this is a spontaneous reaction. Okay? So, a lot going on there, but like I said, this is a plug and chug type of problem. And that's all there is for free energy and pressure. Now what we're going to look at is free energy, and equilibrium. And here's the deal with this. Remember, equilibrium is when the rates of the forward reaction and the reverse reaction are equal. So we have equal rates going on, does not mean concentrations are equal. And what happens, and this is weird, it's just from a thermodynamic point of view, the equilibrium, so equilibrium basically occurs at the lowest value of free energy available to the reaction system. So both of those points, it actually turns out, are the same exact point. Now, I know that that's not going to mean diddly squat to you, so we're just going to jump forward. So what we have is this equation that we just developed for free energy at any conditions, okay? But now, if we get very specific and say we want the equilibrium condition, well, one of the things is the free energy at equilibrium is equal to 0. And if we're at equilibrium, then Q is actually the value of the equilibrium constant. So substituting those into the equation, delta G is 0, and Q is KEQ, then we get this equation. And if we resolve this equation for free energy, then free energy is equal to this new expression, minus RT times the natural log of KEQ. This then becomes our second notebook-worthy equation, so you should put that on AP Chem equation sheet. What does this do for you? Short story is, all this equation allows you to do is calculate what the equilibrium constant is going to be. Okay, basically that's what we get out of this, is we can get the equilibrium constant. Now remember, this is the same equilibrium constant from previous chapters. So, quick little problem with this equation. We know that for iron, okay, so for the corrosion of iron, iron reacts with oxygen in the air and gives us iron oxide. We want to determine what the equilibrium constant would be for this. So we could calculate this, but I gave it to you. So Gibbs free energy for this reaction is negative 1.49 times 10 to the 6 kilojoules per mole. And we just developed an equation that said delta G equals minus RT times the natural log of KEQ. Well, what I want to do is solve for KEQ. Well, this is just a matter of dividing by minus RT, divide by minus RT. So the natural log of KEQ is equal to Gibbs free energy divided by minus RT. And again, these are a lot of plug and chug. So I plug in my numbers and chug them out. Minus 1.49 times 10 to the 6 divided by minus 8.314 times 298. So I don't know if I put that into the problem. Nope, I didn't. This should have been at 25 degrees Celsius. Otherwise you wouldn't have known that. Okay, if you do this, you get the natural log of KEQ is equal to 601. Okay, if you do that math, I suggest you do that. Now, this is where we actually need to solve for KEQ by taking 10 to the 601 power. So it's the second natural log key. So it's the second function of your natural log key. So it's the 10 to the x key is what it really is. Okay? Now, here's the problem with this one, and it's actually why it shows this, because I thought it was interesting. This won't work in your calculators. Okay? So KEQ, whoa, what just happened? Oh, I'm sorry, it's not 10 to the x, it's E. Sorry. I'm not restarting this video. I restart too many. So this is E to the 601, okay, is what KEQ is. And what I was about to say, and I don't know what jumped on me there, this answer actually comes out undefined in your calculators, which means it's shifted very far to the right. And ultimately what that means for you and I is no matter what, our cars will rust, okay, because this is very product favored. In other words, iron really likes to rust according to this. So again, this is going to be a lot of plug and chug. This has got to be one of the worst videos I've created so far. Life's rough. Here's some things to look at though, okay? So we're going to look at some of the chemistry that's going on with entropy, enthalpy, and Gibbs. So we're kind of looking at entropy, enthalpy, and Gibbs free energy and how that affects things. So if you look at these two solutions, I take sodium chloride and dissolve it in water. I take silver chloride and dissolve it in water. What we want to do is calculate the delta G values of this. So I actually want to go back to delta G0, Gibbs free energy, is the sum of the G's of the products minus the sum of the G's of the reactants. And that means we would need to look these values up, and I did that. So the G of sodium chloride is minus 384. This is minus 262, and this is minus 131. Okay, I'm going to assume that you can do this. So the delta G of NaCl actually comes out to be minus 9. Okay, and looking up the values for Ag, this is minus 110, positive 77, minus 131. If you calculate the delta G for that, that delta G comes out to be a positive 56 kilojoules. This was kilojoules. So just looking at those two things, this is spontaneous, this is non-spontaneous. But then, what do you know about these two things? I got a lot written here. What do you know about sodium chloride and silver chloride? And one of the things that you should note about that is sodium chloride is soluble in water. I was writing solubility. Okay, that's soluble. Silver chloride is not soluble. Now, the delta G values actually tell you that, okay? Because this is spontaneous and that's non-spontaneous. Now, the next question that comes up, though, is that solubility due to the heat or is it due to the disorder? So, basically what this question is asking is the solubility, is delta G dependent on the amount of heat or the entropy? And if you look at all the values here, so I listed out the values of enthalpy, entropy, and this is entropy times temperature at 25 degrees Celsius. One of the things that you notice is the disorder is not much different. And the disorder times temperature for these is not much different. And that makes sense because they both produce one ion, or two ions. That would produce sodium and chloride. The other one would produce silver and chloride. So they both, in terms of their disorder, are relatively the same. So that, looking at the heat then, means that this is definitely something that is heat dependent. So this is delta H dependent. Okay? So you can look at these equations, you can look at this amount of free energy, and we can calculate that, but then when we get inside that free energy, this just shows us which term actually affects that free energy more. The next thing we want to do is look at how does the equilibrium constant affect each of these. Okay, and so we're actually going to go back to the equation delta G equals minus RT times the natural log of KEQ. And I'm going to assume that you can plug and chug. So the delta G for NaCl was minus 9 kilojoules. I'm going to assume that you can plug and chug and find K for that. So I'm not going to waste your time with that. So, but the K equilibrium constant comes out to be 1.0036 for NaCl. And for the AgCl, which that heat was positive 56, that equilibrium constant comes out to be 0.97. So I got those by just using that equation. But now look what those two numbers tell you. This is greater than 1. So K is greater than 1. If K is greater than 1, that means we are reactant favored. Here, K is less than 1. That means we are product favored. And in both cases, since AgCl is not soluble, the equilibrium constants make sense. Okay? So this just tells you that, hey, everything kind of jives. And that's all I'm trying to get at here is all of these things jive together in terms of what's happening, okay, with chemical reactions. With that, now you have an assignment. And that assignment, I guarantee, is a lot of plug and chug. So I highly encourage you to actually read your textbook, because we're getting into a lot of plugging and chugging right now and not really caring about what it means.